For next couple of videos, I want to talk about the use of variational principles in mechanics. So that's the topic which we will be taking up. And I will begin with the calculus of variations, which some of you may have encountered in some of your courses. And if you have not, then there is no issue, because I am going to not assume anything that about this. Okay. So let's begin with calculus of variations. I'll give you a typical example of a problem that you may want to study in calculus of variations. Imagine that you are given 2 points which are located at x0 and x1, okay, in the xy plane. Okay, so this starts at some point x0, this starts at some point x1. The x and x coordinates are x0 and x1. Okay, and it's also specified here. It's located. Now you want to let's say you are given a curve like this. Some curve is specified, and we ask what's the length of this curve. So how am I going to find the length of the curve? I'll add up small pieces of it. Okay, let's say this has a length ds, okay, where ds square is given by dx square plus dy square. So ds becomes square root of dx square plus dy square. Okay, so the length of the entire curve would be given by the following. Let me first finish this. So I take the dx out, okay, 1 plus dy over dx, which I call as y prime, and you have a square of it. So that's the differential element of the length along this arc, and the total length of this curve is the integral of ds, which becomes dx, okay, 1 plus y prime square, and of course you have to integrate from x0 to x1. Okay, now let's have a look at the quantity we have in front of us. The length L is a function of the function y of x. Let me write it down first. L is a function of the function y of x. Okay, meaning if you specify a different y of x, if you give a different curve, then the length will change. Okay, of course that's an obvious statement. So what I'm saying is, if instead of this one, if I give you another curve, let's say I gave you this curve, then you evaluate this quantity again on the right hand side, the integral, and you'll have to substitute y prime for this curve, take a square of it, do the square root, do the integral, and you get another value of L. Okay, so L is a function of the function of y of x. It's just like for ordinary functions, when you give a number, the function produces a number. So let's look at this. What is f of x? Let's say f of x is x square. Okay, so you give a value of x, so you give a number, let's say x is 1. Then what you get is again a number back. You get x square is 1, you get f of x is 1. So you input a number, you get a number. But here L has a different nature. You input a function and you get a number. Okay, so this is not a function but something different. Okay, and these quantities are called functionals. Okay, so for me, that quantity above L is a functional. And what's a functional? Functional is a function of a function. So I'll make this thing as a prototype definition, prototype of a functional. So I'll define functional to be a function of a function. So let me just write it down. Functional. Okay. A functional f is a function of one or more functions. Okay, so that's the definition of functional, and just pay attention how we have arrived at such a definition. It was because of the prototype example that we took. Okay, and it is standard to notate or denote by a functional, for example, in this case, the L as the following. So you write L with a square bracket y. So L is a functional of, in this case, y, where y denotes any curve between these 2 points. Okay, I'll give you another example. So that was example number 1. Let me put it down here. This was length of a curve. Length of a curve between 2 points. You can think of several such problems in which you will have a functional, and one such I'll give you now. So it's surface of revolution. So let's see here. So the thing is this. Okay. This is your x-axis, this is your y-axis, and between 2 points you are given some curve. Okay, some curve is given to you. Oops. Let's say like this. Now what we want to do is, so let's say, before I tell you what we want to do, let's say this is located at x0, this is located at some value x1. Okay, now what I want to do is take this curve and rotate it about the x-axis. Okay, so when I rotate it about the x-axis, I get, it will be difficult for me to draw on this slate. Let me try anyway. Not bad. It's fairly good. Okay. So when you rotate it, this is what you'll get. Okay. So there'll be a flat end here. There'll be a flat end there. Which with this bad hand drawing, it's difficult. But anyway, let's now. You can ask, what is the area of this revolution of this curve? So whatever shape, pot kind of thing you are looking at, what's the area of the surface of this pot? Okay, and let's find out what it will be. Again, I take a small element ds here. Okay, and then I make a differential area element here. Okay, this looks bad. Okay, so that's the small area element that I'm looking at. Okay, which is, if you look from here, it is this ds is located a distance x away from this line. So if you look at the dA, it will be 2 pi x, sorry, it's not x, it is y, 2 pi y. So this is y direction. Okay, so the radius of the strip is y, so the area element is 2 pi y times ds, and we already know what ds is. Ds we found to be dx 1 plus y prime square. Okay, that's what we saw in the previous example. Okay, so if I want to know the area of this surface of revolution, it will be 2 pi times integral dx y square root of 1 plus y prime square. Okay, and to emphasize that this is a functional, I write here y. Okay, so again as before, you'll get area will be some number, right? It will be some number, it will have some value, but that number you are going to get by specifying a particular curve. So if you specify this curve, you get some value. If you specify a different curve, let's say you specify a different curve like this, then you'll have a different area of revolution and you'll get a different number of number for a of y. Okay, so this is another example of a functional. Okay, I'll give you one more example. Suppose I give you an integral over one variable dx f of x times some u of x. Okay, where I will specify f of x for you. So let's say I fix the f of x to be say e to the minus x, or e to the minus, let's say e to the minus x. Okay, now this integral now is a functional of u. Okay, if you choose u to be something and you do the integral, let's have some limits, let's say 0 to 1. Okay, these limits are fixed. So if you take some function, this function is specified for you. As you change the function u of x, you get different values, and that's why your integral on the right hand side is a functional. Okay, so this is a functional of u, functional of the function u. Okay, with different choices of u, you get different values. Now it will happen that we will be interested in the maxima or minima of functionals. For example, you could be interested in asking what is that curve that will give you the minimum surface area of revolution, or in this example, given these 2 points x0 and x1, what curve gives you the minimum length of the curve. Okay, so for what function y the length gets minimized. Okay, that could be a question that you can ask, and these are similar to the questions that you ask when you are studying maxima and minima of ordinary functions. You ask at what point you will get a maximum of this function. Now remember the point, for example here in this example x was 1. Okay, that point is replaced by the function. So you ask in the case of functional, for what function you get minimum of the functional. Okay, that's about functionals. That's what I wanted to say. Maybe I should write it down. I think I should write it down. So the questions we will be generally interested in asking in this case of functional is, for example, what curve gives the shortest distance between 2 points. Between 2 points. Let's say in the xy plane, for example, or xyz. Or what curve gives the minimum surface area of revolution? What curve gives the minimum surface area of revolution? Okay. Now, before I go into looking for these questions for functionals, let's review what we know about the maxima, minima, and all these things for ordinary functions of n variables. Okay, so that's what I'm going to do. Then it will be simpler or easier to move to functionals. So let's look at now, maybe some color will be nice. Let's go to next page. Review of maxima of ordinary functions. Okay. So imagine we are given a function f which depends on n variables x1 to xn. Okay. Then about a regular point I can always do a Taylor expansion. Okay, if there are no singularities there, then let's say I want to expand it about some point x bar, which is basically this set x1 bar xn bar. Okay, so that's point x bar is really all these things evaluated at that point. Now you know that I can expand it around x bar as follows. So I get fx bar, then I have terms with the first derivative del f over del xi, then xi minus xi bar. Okay, where you have a summation over I implied by this repeated indices. Then you get second order terms delta 2 f over delta xi delta xj xi minus xj, sorry, xi minus xi bar, and then you have xj minus xj bar. Okay, plus higher order terms. And you can easily check that if you expand this for case of two variables, you get f of x y as, let me put as x bar y bar plus del f over del x minus x bar plus del f over del y minus y bar. And here you have three terms. When I is x, I mean, let's say xi is x, so it gives you delta 2f over delta x square. So there should have been a factor of half here, which I missed. So you get half delta 2f over delta x square. This gives x minus x bar square. Then you get the second term, which has delta 2f over delta y square, y minus y bar squared. And the third term is where you have one of them as x, another one is y, but they are going to come twice because there is a summation over I and j. So you get a factor of 2 x delta 2f over delta x delta y, x minus x bar and y minus y bar, and plus all the higher order terms. Okay, now if all the partial derivatives, del f over del x, del f over del y, and in case of multiple variables, all the partial derivatives, okay, they all are 0, then you call that point as a stationary point. Okay, so let me write. If all the del f over del x I are 0, which is equivalent to saying that your gradient of f is 0, then that point is called stationary. Okay, let's say this happens at some point x bar, where x bar is x1 bar, x2 bar, and so forth. Then this point is called a stationary point. Okay, it's stationary because if you do a if you move away from point x bar, the value of the function f does not change to the first orders. Because these are all 0, your df is 0. Okay, so there are no first order changes. So point has not, the value of the function has not moved from its original value, so it's stationary there. So that's why it's a stationary point. Now, depending on what these terms are doing, or these terms are doing, these coefficients are doing, you may or may not have a extremum there. You may or may not have a maximum at that point. Okay, so if the function if at this point the function is maximum or minimum, then you say the point is extremum point. Otherwise, it may happen that these derivatives are all 0, and then there is no maximum or minimum, and it's a saddle point or point of inflection. Okay, that's good. That's fine. Now, I would be interested in asking, for example, what if I'm given a function, okay, and I'm looking for its maxima and minima, or the stationary points. Let's say I'm not interested in knowing whether it's a maximum or a minimum or a saddle. I'm happy with knowing whether it's a stationary point or not. Okay, so in this case, this is fine. You just take the derivatives, and if the derivatives all the derivatives are 0, then you say that it's a stationary point. But what if all the variables x1, x2, and so forth, xn, they are not independent of each other, but there are conditions which constrain them? Then how do I find out where the maximum or minimum, or let's say more generally stationary points are located? Okay, so the question I'm asking is the following. I'm interested in finding the stationary points of functions with additional conditions. Okay, that's what I would like to ask. For example, I may let's say you are given some function f of, let's say, 2 variables is xy, okay, and you are given a constraint that x square plus y square should always be 1. Okay, and now I ask, where are the stationary points located for the function f given phi? Okay, let me write it more neatly. let's say phi is specified to be this. Okay, x square plus y square equal to 1. Okay, so these are the kind of things which we want to ask, and I'll give you the answer to this. And actually, it's easy to see why that is the answer. And you can also look at the book by Courant and John, Introduction to Calculus and Analysis, Volume 2. I think it's Volume 2. Yeah, there you can find a good discussion on the subject. So let me state this first. Maybe I should, yeah. Probably it will be nicer if I move to the next page. So method of undetermined multipliers. I'll give you the answer, and then we'll see why that is an answer. So question is the same: stationary point of a function with some additional constraints. So let's say I have a function f which depends on several arguments, and let's say there are total n of them, which are x1 to xn. Okay, and the constraints are the following. You have in total let's say m constraints, and m has to be less than m. Okay, and let's say we denote them by f1 of x1 to xn being 0. Then you have some other constraint phi 2, which constrains all these variables, and you have phi m, okay. Now we are asked to find the stationary point of f. So to find the stationary points, where is it? Yeah, to find the stationary points of f, okay, we introduce m multipliers. So one multiplier corresponding to each of these. So let me denote by lambda 1, lambda 2, and so forth up to lambda m, a total of m multipliers. This is step 1. So you introduce these multipliers, then you construct a function, a new function actually, f, which is a function of all your variables which you had originally, and then it also is a function of all these multipliers. Okay, and the definition of the function is the following: f is your original function plus lambda 1 phi 1 plus lambda 2 phi 2, so forth, lambda n phi n. So that's the new function that we have constructed. Now what we do is the following. Remember, if all the phi's were 0, meaning there were no constraints, so let's say all these were there were no constraints at all, so let's say these were all not there, okay, then your function is just f, and to find the stationary points you have to take the partial derivatives of f with respect to all the variables and equate them to 0, right? But now in this case what you have to do is again take the partial derivatives of capital F with respect to all the variables and equate them to 0. Okay, so it's roughly, it's exactly like the original thing, but instead of acting the partial derivatives on small f, you act them on capital F. So let me write it down. Equate the partial derivatives of f to 0, and these derivatives have to be evaluated for all the variables in the problem. Meaning, let me go to the next page. So you have to calculate delta f over delta x1, then you have to calculate and equate it to 0. Then you get delta f over delta x2, put it 0. Delta f over delta xn, put it to 0. Calculate again delta f over delta lambda 1, put that equal to 0. Delta f over delta lambda m, and put that equal to 0. Okay, so how many equations we have now? N of these equations I have, and m of these equations I have. So I have total of n plus m equations. Okay, so there are a total of n plus m equations coming from here. And how many variables do I have? I have again n plus m variables. Okay, n for the x's and m for the lambda. So there are total n plus m variables. Now n plus m equations, n plus m variables, this system can be solved. Okay, so I can find out all these things. But now the question is why this is the solution of our problem. So let's go back. Let's see what delta f over delta x1 gives. Delta f over delta lambda 1 gives. Let's put generically lambda I. This gives you phi I. Okay. And when I'm equating to 0, this is the condition I had originally, right? So these are m equations, and I have phi I equal to 0 coming from here. Okay, so this anyway I needed to solve. And then you have the partial derivatives with respect to x1, x2, and so forth. And together with these conditions, you get back your delta f over delta x1 equal to 0, or delta f small f over delta x2 equal to 0. Okay. So that is why this system of equations provides you the stationary point of the small f together with the conditions. Okay, that's why this constitutes a solution. And these lambda i's are called Lagrange multipliers.